Okay, we will continue with the topic of rotational spectroscopy for just about 10-15 minutes, and then we will move on to vibration. You already have received the assignment. Maybe the last two questions we haven't done it yet, but we will go into the problem of today as well as the next class before. Wednesday happens to be a holiday, but I guess we will have to meet so that we have the tutorials that day. So I have an option of doing a tutorial on Friday or doing on Wednesday, but I think I'll do it on Wednesday because that way you still have questions after the tutorial. You have one more day on Friday when you can check with me and we can have the doubts clarified. But if I do it on Friday, I'm gone, and then you, and not only that, I'm gone for a couple of days. I won't even be around. So after the Friday class, it will be hard for me to catch, for you to catch me. So I'm leaving on Saturday and coming back on Wednesday. So it's better that we do the tutorials on Wednesday. So if you have questions still to ask me, you have one more day that you can do. The question is, when do we do it on Wednesday? I don't know whether you want to do it at 5 o'clock and we're doing it now. We could do it earlier if you want. What's the good time? Oh. Morning is already taken by 101. So morning 8:30 to 9:30, I have a tutorial for 101. It's not that simple. 10 to 1 I have a PhD exam I have to conduct. So the earliest I can give you is about 3 o'clock, in case the exam extends a little bit long. PhD exam we have no control. It all depends on how the student does. So 3 o'clock is something that you like, 3 o'clock or 4 o'clock. 3 to 4, 4 to 5. I think the voice vote makes it like 3 to 4. We start at 3 p.m. It also depends on how things go to the end point. We don't know. We will see where the end point is. But we will start at 3. So I'll be here at 3, and it's a regular class. So it means that white sheet of paper and passing around will be passed around. So attendance is compulsory. So we have a tutorial that day where I will essentially go through the questions I have given you. And we will discuss that, plus a few more questions that are given at the back of the chapter in Banwell. We will look at some of those questions too. So that if you have answered these questions, you basically, in my opinion, got the basic information and the basic stuff related to these topics. So that's basically what I would like you to do. But do try to work out the problems. And as you can see, there's enough that I have done on Wednesday. So I will do little talking on Wednesday over here. At 3 o'clock, I'll probably ask one of you to go up to the board and start solving the problems so that you do the talking and I do the listening at that point in time. Of course, I will fall in and give you the clarifications in greater detail if that's required. But in a tutorial, I would like some of you to come up and start answering the questions that we have, with the course assurance that I will provide you the more detailed clarifications if you so need. We will do it that way. I am hoping that there will be volunteers that day who will want to come up and solve the problem. If there are no volunteers, then of course we go by the usual draw of lots. The reason why I am saying draw of lots is essentially to warn you that if your name comes up, then you have to go up to the board. Which means that you better solve the problem and be ready with it, because it could be your turn to come up and solving these things. Okay, so what we did in rotational spectroscopy is we looked at the diatomic, and that's basically what we did. We looked at the diatomic, we looked at the rigid rotor approximation, we wrote down the energy equation, we wrote down the equation that tells me how the spectral lines sort of pan out. We saw the 2D spacings, that will be at equally spaced lines. Using that, we could calculate the bond distance and so on. Then we said, well, it's not really a rigid rotor, it could have centrifugal distortion. And then we chose the centrifugal distortion constant, which essentially was writing out the energy equation as a polynomial in j to j plus 1. So earlier we had j to j plus 1 multiplied by b. Then we said, well, it's actually minus d to j plus 1 whole square, which was the centrifugal distortion constant. And because of which the lines will no longer be 2b spaced, but they will start to get narrower and closer and closer. And that's an effect because of the centrifugal distortion. And as we had discussions the other day, if you put a really high j, even this equation is not good. You have to have b to j plus 1 minus d to j plus 1 whole square minus a plus h into j to j plus 1 whole cube, and goes on. There are situations where people have used 7, 8, 9, 10 term polynomials to explain what they are seeing in an experiment. As far as this course is concerned, we will stick with b and d. We won't get anywhere beyond it. In other words, the first centrifugal distortion constant. So after that, it's only a fine structure. The concept you already have learned. The centrifugal distortion actually decreases the spacing, increases the bond length because of the distortion that there is, and using all this information, you can get a lot about the nature of the bond. In fact, I even said that by a combination of B and D, the rotational constant B and the centrifugal distortion constant D, what can you estimate? The vibration frequency. Right? We said that is 4b cubed over omega squared equals d. So if I knew d and I knew b, I can actually get omega, which is the vibration frequency. But what am I doing? I'm actually doing rotational spectroscopy. I'm not even doing vibrational spectroscopy. But I'm still giving you information about the bond length, the bond strength. And that is simply because the bond strength in a way is related to the centrifugal distortion. Stronger the bond, more difficult it is to distort. Weaker the bond, more easy it is to distort. Therefore, a high value of D actually tells me the bond is actually quite weak. A large value of D tells me that. A small value of D tells me that the bond strength probably is quite high. So in a way, by using information from B and D, I can actually get information about the strength of the bond. Not very accurate as vibration spectroscopists can give you. It's still a good estimate, and you will get it like within 5 to 10%, which is pretty good really. We also saw the effect of isotopic effects. If you put a heavier atom, what does not change? The bonding does not change. What does change? The reduced mass changes. And using that information, you can actually confirm your J numbering. And in polyatomic, you can actually use the isotopes to get more moments of inertia and to be able to get the extra parameter that you have to deal with in polyatomic. Even water, for example, you need 2 bond lengths and 1 angle. But how many moments of inertia can you possibly get? 3. Not too bad. But suppose I go to methane, how many bond lengths do I have? 4 bond lengths, 1 angle, right little angle. How many moments of inertia do I have? 3. Now I am underdetermining my problem. I have only a few moments of inertia and many parameters to decide. So what do? I take isotopes and start getting more moments of inertia. But when I put isotopes, what am I not doing? I am not changing the structure. Therefore, this method works. We will not do polyatomic because it's quite messy, but we will just see why it is messy. It's messy for the following reasons. Let's take a BCl3 molecule. I ask you to calculate the moments of inertia for this system. What will that be? Well, there's one axis this way, another axis this way, and a third axis this way. But the 3 mutually perpendicular axes, I'm going to calculate the moment of inertia around that. For this axis, what's the moment of inertia? The axis is projecting onto the board. And given the moment of inertia is simply going to be MIRI squared. So the boron is sitting on the axis and therefore will not contribute to a moment of inertia. What about this fellow? It's going to be MCl into R. If I just call this R. And then you have MCl plus MCl, this is the same. Therefore, basically, you're going to have that moment of inertia. And of course, you know the mass of flow is And like in new art, then of course I know the moment of inertia, but generally when you do these experiments, you're not supposed to know art. You're supposed to find out art. And that's how you do it. What about this axis? We will see how to label them later. Let's take this axis. If you do this, what happens? Boron and chlorine are sitting on the axis, and therefore they are not going to contribute to the moment of inertia for that. But what about these two chlorines? Yes. And what's the distance you got to take? It's actually the profile distance from the atom to the axis. So this is what we need to do. I know this angle is 60. I know this angle is 60. Therefore, if this has to be R, how much would this be? 0.87 R. That's just my sine 60, I will get that. 0.87 R. It's going to be this. Then I have to square this. And when I square this, what do I get? 0.75 R squared. Square this, I get 0.75 R squared. And therefore, the moment of inertia along this axis is simply going to be mass of chlorine into 0.75 R squared plus one more time. Therefore, what do I get? This was 3, this was 1.5 mass of chlorine into R squared. The third one is by this one, and here what do I get? It's mass of chlorine into R squared plus mass of chlorine into this distance squared plus mass of chlorine into this distance squared. Work it out. It will be 0.5 R, 0.5 R. You will again get for this axis also 1.5. So I now have the three axes, one of which has a moment of inertia around it, which is 3 mcl r squared. Other one has 1.5 mcl r squared. The third one has 1.5 mcl r squared. Therefore, I have two moments of inertia equal. The third one is not equal. Now, by convention, the one that has got the largest moment of inertia, we are going to call them as IC. Just a convention. So we will call this as IC. This is IB and this is IA. The IA is the one that's the smallest. The IC is the one that's the largest. And IB is in between. But in this case, IB and IA are equal. Therefore, the situation I now have at hand, in this case, is IC greater than IB equal to IA. Do it for benzene. Do it for metal iodide. And you will see that there are cases both in benzene and in metal iodide. You will find that two moments of inertia will be equal and one of them will be the unequal part. In a linear molecule, what happened? Two of them are equal, but what happened to the third fellow? It's 0. So that's a special case, and we call that as the linear system. But in non-linear system, we still can have a situation in which two of them are equal and the third one is not equal. Now we have two possibilities. The unequal guy could be the largest guy. The unequal guy can be the smallest guy. That's also possible. And we call such molecular systems in which two moments of inertia are equal and one of them is not equal as a symmetric top. In fact, this one is called the prolate symmetric top, and this one would be called as the oblate symmetric top. I won't push you so much into remembering whether it's prolate or oblate, but I would still want you to recognize that the molecule belongs to a symmetric top. That's important for me, because it's very easy to get confused as to which one is prolate and which one is oblate. But what I really want you to do is to be able to tell me that it is a symmetric top. How do you know the symmetric top? You have to figure out the moments of inertia by simply calculating them. Metal iodide, it's not so easy to do it. It's because the molecule jumps out in three directions. This is a planar molecule, it's easy. In metal iodide, it's not so. So what we then do is to start using the concepts of symmetry, which you have learned last semester. And what does symmetry tell you? Symmetry tells me that if the molecule has a CN axis of rotation, the molecule has a Cn axial rotation where n is greater than 2, you'll find two moments of inertia will be equal and one will be unequal. The symmetry of the molecule essentially provides me this information. What's the axial rotation in BCl3? It's got a C3 axis. Of course, it's got a C2 axis, but what's the largest axis of symmetry in that? C3. Therefore, it is n greater than 2. Therefore, that molecule perforce has to be a molecule that's going to be a symmetric top. Methyl iodide. What is the symmetry axis for that? Methyl iodide. Carbon, hydrogen, 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 and an iodine on top. The axis running through carbon and iodine actually is the C3 axis of symmetry. Therefore, it is a C3 axis of symmetry. You don't have to sit down and calculate all the moments of inertia. You know that this must be a symmetric top. Because if the molecule has an axis of symmetry which is greater than 2, it must be a symmetric top. What about methane? What do you think will happen to methane? What's the axis of symmetry for methane? C3. But then methane belongs to a tetrahedral system and belongs to a cubic point group, right? You saw that. What's the other structure that belongs to a cubic point group? Tetrahedral is one. Remember I told you there were two structures which you can actually fit inside a cube. A tetrahedral is one. What's the other? Octahedral. So the octahedral system and the tetrahedral system actually belong to a symmetric point group, a cubic symmetry. And such systems have something even more nice. And what is that even more nice? All three are equal. And when all three are equal, we call such systems as belonging to a spherical top. So you have a linear molecule, and what's the specification for a linear molecule? IC equal to IB, IA equal to 0. What's the other possibility? IC equal to IB, not equal to IA, but greater than IA, or IC greater than IB equal to IA. So the unequal guy can be the greater or the smallest one. But there are two of them equal, and when I have two of them equal, then I'm basically dealing with a symmetric top. Third possibility, and what's the giveaway for a symmetric top? The molecule must have an axis of symmetry Cn where n is greater than 3. If I have n greater than 3, then I know it has to be a symmetric top. Methane, a tetrahedral system. Any molecule that belongs to a TD point group, the tetrahedral point group, or any molecule that belongs to an octahedral point group will have IA equal to IB equal to IC and will therefore belong to a spherical top. All three moments of inertia are equal. Why am I asking for all this? Why do I need all this information? When you wrote the energy equation for a diatomic, what was the energy equation? E equals B into J plus 1. Simple. When I start writing the energy equation for a polyatomic molecule, it's not that simple. Because I just don't have one rotational constant. The rotational constant depends on the moments of inertia. I have two different rotational constants over here. These two paired and one here. So therefore, the energy equation now will have to involve two different rotational constants, one depicting the IC-IB combination and one for IA. Spherical top is again simple. It behaves like a linear molecule because IC equal to IB equal to IA. I only have one rotational constant essentially because all the three moments of inertia are equal. What's the worst case scenario? IC not equal to IA, IC not equal to IB. I'm already stammering when I say that, it is so complicated. IC not equal to IB, not equal to IA. So which means there are three moments of inertia and the energy equation is going to be really complicated. And we don't even give it in books. We just leave it to those people who want to kill themselves doing the rotational analysis for a molecule of that type to write out their own equations and solve their own equations. It's pretty complicated because you have three. And those are cases where you have IC greater than IB, greater than IA. None of them being equal. and you call that as the asymmetric top. Any guesses? What should be the symmetry specification for an asymmetric top? Based on what we have done so far. What should be the symmetry requirement for a molecule with an asymmetric top molecule? Cn, axial symmetry, but what should n be? 2 or lower. When I said it should be greater than 2, I was already laying the ground for the molecule to be a symmetric top. So if C3, C4, C5, and so on, it should be a symmetric top. But if it has an axial symmetry which is C2 or C1, then I am talking about a molecule with an asymmetric situation that IC not equal to IB, not equal to IE. Example? Simplest example. Why it goes that much? Water has a C2 axial rotation. And we said there is a molecule has a, and work out the, just sit down and work it out as to what your moment of inertia must be for water. And you will find IC not equal to IB, not equal to IA. Which means any molecule is got a C2 axis as the highest order symmetry axis, or C1 will not be in any of these classes, it will be the asymmetric top, and will therefore have 3 different moments of inertia and therefore 3 different rotational constants. The energy equation is quite complicated, and you basically have to deal with such things there. So any molecule that is got a C2V point 2, C2H point 2, or a C1 point 2, they will all be molecules which are going to be actually in asymmetric top. So you see all the symmetry concepts you learned last time actually comes in pretty handy when you start to analyze rotational spectrum, and that's how you basically do all this. So you look at the molecule and if you do an experiment and you get 2 moments of inertia equal, third one not equal, you immediately know you are looking at a molecule with a certain degree of symmetry. Straight away you get symmetry information. You look at a molecule and you get all 3 moments of inertia not equal. Then you know you are looking at a molecule with C2 axis or low. Of course, there is one more. It can either be a Cn greater than n equal to 2, which means n3, n4, and so on, or a molecule with an S4 axis will also come under the class of a symmetric top. Any molecule with an S4 axis symmetry that you remember? What's an S4 axis? Improper axis of rotation, right? And what's an improper axis of rotation? You rotate to the C4 rotation followed by a reflection to give me the original molecule. Now, any molecule, remember, that has a C4 axis. Behaves like an organic technology. So, which means this hydrogen is outside the plane of the board, this hydrogen on the other side sway, whereas these 2 hydrogens are in the plane. So, what do I do now? I take that and rotate it to 90. When I rotate to 90, then these 2 guys come here, but then this guy will walk on the other way. But then after doing a reflection, right here, I will get back the structure. But this is a molecule that will have an S4 axis of rotation, an improper axis. And if I have an improper axis of rotation S4, that's another tip off that the molecule would actually belong to a symmetric top. That is, I see 2 of the moments of inertia being equal, and the third one not being equal. Of course, as I said, slowly get into this habit of fixing into your mind as to which one would be a prolate and which one would be an oblate. At this point in time, at least for this exam, I'm not going to bother you with that. If you just tell me it's an symmetric top, you will get your marks. But in the final exam, you still have 2 more months. By that time, you should start looking at the molecule and figure out which one of them should be the asymmetric top and which one, the symmetric top which is prolate and symmetric top which is oblate. I'm not even going to mention it now. It all has to do with which of them has, I wrote here, that's prolate and that's oblate. But in an exam, I know what will happen. Suddenly, you will not remember which one is which. But given time, pick up examples of molecules and then realize for yourself, oh, this molecule is prolate, this molecule is oblate. And and then you'll be able to remember. So by the time we are through to the final exam, there should be enough time for you to have internalized this concept of prolate symmetric torques and oblate symmetric torques. In the final exam, yes, I will insist that you tell me what is what. But for the exam next week, if you can tell me, if I give you a bunch of molecules and I asked you what do these belong to in terms of the classifications of rotors, and I'll be more than happy if you tell me that it is a symmetric torque. Of course, I'll be more than happy if that really is a symmetric torque and tell me it is a symmetric torque. So you got to get these those things right. Okay. But this is basically what. So polyatomic spectroscopy, rotational spectroscopy is rather complicated really because of all these little things that are. First, I have to deal with more than one rotational constant. And in the extra rotational constants I'm really getting are not of complete use because they are not enough. Because in polyatomics I have to deal with a lot more bond distances, bond angles and diagonal angles. And these 2 or 3 rotational constants that I get from the 2 or 3 moments of inertia, no good. And if I am looking at a symmetric torque, a spherical torque, all 3 are the same, and therefore I get one value. But I need to get a lot more numbers to be able to fix my bond distance, bond angles, and my diagonal angles. So you got to do a lot of isotopic work, and isotopic work is not straightforward because you got to prepare the compound with the isotope in the right place. So it's not a question of just taking a molecule off the shelf and doing it. You got to take the molecule, prepare the isotope with the isotope in the right place, purify it, then do your experiment and so on. So it's a pretty involved stuff, and I have the greatest of respect for people who do rotational spectroscopy because it's really hard work. But at the end of the day, the sort of data that they give you is extremely important, is extremely useful and extremely accurate, particularly when you're looking at very deep complexes such as the hydrogen bonding, interaction and so on. They can really tell you where the water is sitting in that molecule. Why? Simply because the moment of inertia is very easily able to pin down after you have got the data. You'll be able to pin down as to the exact location of the water molecule sitting on some surface and in what way it is oriented and so on. So the sort of data you get is extremely useful in deciding such big interactions. Okay? So this is basically what I would like you to learn, what I would like you to know as far as rotational spectroscopy is concerned. Work out all the problems that I have given you. Again, I warn you, don't look at the problem and say, oh, it looks simple, I know what to do. It's not that. When you start working out, you'll find there are enough pitfalls where you can just, it's like quicksand, you get in and you won't be able to get out within 1 hour of the exam. So please work it out and ensure for yourself that you know exactly how to solve these problems. They're not very difficult, but you just have to do it a few times and internalize the actual methodology or prescription by which you solve these problems. Now let's move on to something else. And that's going to be the topic of vibrational spectroscopy. Which is something quite close to my heart because that's what we do in looking at molecular structure and information. We're basically looking at vibrational spectroscopy. And I'm also sure that most of you have already done a few experiments on infrared spectroscopy. You have got your vibration data and you have been able to analyze them to get functional group information and so on. And that's basically what you're going to be looking at now. What you did in the lab, I think you recorded the spectra of a few organic molecules, and from the spectrum you were able to decide what the functional groups were. Now that's one application where you're essentially using the infrared spectra as a characterization tool to see what groups you have in the molecule. Oh, but what you can do, and that's the organic chemist way of looking at the problem. The physical chemist way of looking at the problem is to use the vibrational data to start getting information on the bond strength, the nature of bonding in the molecules and so on. And we will see how both these pieces of information can essentially be obtained